Now I'd like to tell you some facts from algebra and algebraic geometry. So far, everything I've told you has been kind of basic. You know, it's all followed from the definitions I've given you in linear algebra. Now I want to tell you some things which are more non-trivial and harder to prove. So let's recall some facts from about commutative rings. So for example, you can find them in the book Herstein Topics in Algebra, which was a kind of default algebra textbook when I was a boy. So a unit in a commutative ring R, and the rings we're going to care about are polynomial rings over a field. So unit is some element A in R such that there exists another element B in R with A, B equals 1. So a unit is just something which is invertible under multiplication. Secondly, an irreducible element A in our ring R is such that if A equals BC in R, then B or C is a unit. So this is basically invertible. If you like, you can think about this as meaning prime. So if you did this in the integers, then the irreducible elements would be, well, prime numbers and minus prime numbers and plus or minus 1. Now we call our commutative ring R a unique factorization domain. We probably want to I'm not sure if this goes in the definition or not, but we probably want irreducible elements not to be units. So you want to exclude 1, for example. We call R a unique factorization domain. So UFD is the usual acronym. If firstly R has no 0 divisors, so you can't write 0 as the product of two non-zero elements, and every element has a factorization into irreducible elements, which is unique. It's not entirely unique. It's unique up to order, up to reordering your finite number of irreducible elements, and multiplication by units. Okay, so this is a bit like saying every number in the integers can be factorized into primes, a product of primes, and that factorization is unique up to reordering your primes, and, well, because in general rings you don't have a good notion of positive or negative, so you might be saying, well, 6 is 2 times 3, it's also 3 times 2, so you can reorder things, but also you could replace that by a minus 2 times a minus 3, because from the point of view of the ring, minus 2 and minus 3 are just as good prime numbers as 2 and 3 are, and so here we've multiplied our irreducible elements by units. Okay, so basically this is about some kind of prime factorization. Right, so here is the theorem we're going to care about. We let F be a field. So then the polynomial ring f of x1 up to xn is a unique factorization domain. And the units are the constant polynomials f take away 0. Okay, so we can always factorize polynomials into irreducible or, if you prefer, prime factors. Okay, so that says that over any field we're allowed to factorize polynomials into pieces kind of as far as they go. So over the complex numbers you'll be used to being able to factorize things in one variable into linear factors. That's not true for polynomials in higher numbers of variables. You'll get kind of irreducible polynomials of any degree. Okay. Any questions on that? All right. So a field F is called algebraically closed if every polynomial p of x in just one variable, not in many variables, factorizes into linear factors. So C is algebraically closed. On the other hand, the reals is not algebraically closed. So, for example, the polynomial x squared plus 1 doesn't factorize So you can't factorize x squared plus 1 into linear factors over the reals. You can, of course, factorize it as x plus I, x minus I over c, but that's not happening within that field R. The finite field ZP is with P for period prime. This is not algebraically closed. So in fact, every field has an algebraic closure, which is the smallest algebraically closed field you can embed it inside. And you can get it by essentially taking your field and then adding in zeros to every irreducible polynomial. So the complex numbers is the algebraic closure of R. There's also an algebraic closure of the rationals, which is a subfield of C, but a countable subfield. And this has an algebraic closure as well. And we prefer to do algebraic geometry over algebraically closed fields because of the next theorem. So it's got an exciting name. It's called Hilbert's Nullstellensatz. Okay, that's a German word. It just means zero theorem. So, but that sounds less exciting. So the condition is this. We let F be an algebraically closed field. And let's suppose big P and big Q are polynomials. So it's a convention that you use square brackets for polynomial rings. I should have made that a bit clearer. Let F be a polynomial in n variables x1 up to xn. So then, the set of zeros of P set of points x1, xn with round brackets in f to the n, such that big P of x1 up to xn equals 0. So we want to know when are the zeros of P equal to the zeros of Q. So when is it equal to a set of zeros x1 up to xn in f to the n, such that Q of x1 up to xn is 0. So these zeros are equal, zero sets are equal, if and only if, I'll give you two equivalent conditions. Firstly, P divides Q to the m, and P divides, and Q divides P to the m, well, some other m primed, for some m and m primed greater than 0. That's one way of putting it. The second way of putting it is that P and Q have the same irreducible factors in f of x1 up to xn. By that I mean really up to multiplication by units and up to order. But possibly with different multiplicities. This is saying P and Q have the same prime factors, but those prime factors can occur to different powers in P and Q. So it's a bit like saying, well, 6 and 12 have the same prime factors 2 and 3, but the 2 appears to different powers. And well, you can see these two things are equivalent because if P and Q have the same prime factors, then if you take a large enough power of Q, the same prime factor will appear to at least as large a power in Q to the m as it will in P, and so P will divide Q to the m, and vice versa. Okay, so this is only true for algebraically closed fields. So then the proof is beyond the scope of the course. And maybe the theorem itself is beyond the scope of the course, but what I care about really is the interpretation. Well, so one consequence of Hilbert's Nullstellensatz is that if C primed is a curve in CP2, which is defined by a polynomial, P of x, y, z, homogeneous, and let's say with no repeated factors, so the irreducible factors of P are not allowed to occur more than once, then C primed determines P up to rescalings. P goes to lambda times P. For lambda in the complex numbers, take away 0. The analog's true over any algebraically closed field. So what that really is saying in here is that if we, a good way of making sure we don't have to care about different multiplicities in P and Q is that if we insist that P and Q have each irreducible factor appears with multiplicity 1, there are no kind of squared factors, so it's kind of square free, then basically we could take the m and the m prime to be 1, and that P and Q would be proportional by a unit, which is just a non-zero constant in your field. Okay, so this is again the kind of tension between geometry and algebra. So this statement is a statement about geometry. It's about spaces. It's that this hypersurface equals that hypersurface in your affine plane f to the n. These are statements about algebra. And the theorem is kind of saying that the algebra is equivalent to the geometry. If you know it, always if you know the algebra, you can deduce the geometry, but now we can go backwards. If we know the geometry, we can deduce the algebra. And so being algebraically closed in your field is kind of a condition for a lot of algebraic geometry to work nicely. Because otherwise, when you pass from your polynomial to your zero set, you lose information. So that there's lots of things in RP2 which could be defined by different polynomials, and you wouldn't know the difference. For example, in RP2, you get that x squared plus y squared plus z squared equals 0. That's the empty set. It's also x squared plus 2y squared plus 3z squared equals 0. So there are two different polynomials with the same zero set. Those two polynomials are not the same up to repeated factors or whatever. So the Nullstellensatz is false for R. So any questions on that? All right, so let's have a section on 2.3 on irreducible and non-singular curves. So we're going to do this in CP2. We're going to use this notion of irreducible factors and factorization and the Nullstellensatz to see how we can break a curve into some kind of nicer pieces. Let's make a definition. If we let C be an algebraic curve in CP2. So you can also make sense of this in C2. So then C is defined by a homogeneous polynomial P of x, y, z. So taking P to have no repeated factors, because having a repeated factor doesn't really change the zero set. If a factor of P is occurring to power 3, you could replace it by the same polynomial with the power 1, and you'd still get the same set of zeros. So taking P to have no repeated factors, that's kind of equivalent to taking P to be of minimal degree to define that curve. Taking P to have no repeated factors, then P is determined by C uniquely up to rescaling. Rescalings P maps to lambda times P for lambda in C take away 0. That's a consequence of the Nullstellensatz. Okay, so firstly we say that the degree of C is the degree of P. So okay, we now associate an important number to our curve. It's some kind of measure of its complexity, really, as a subset. And it is intrinsic to the curve C. It doesn't depend upon any choice of polynomials to define C because of this fact here. And we call C irreducible if P is irreducible. In other words, the only factors of P, factorization in the ring C of x, y, z of complex polynomials and 3 variables, the only factors of P are constants, so non-zero constant polynomials, and multiples of P, meaning multiplication of P by a non-zero number in the field. Okay, now we call C irreducible if its polynomial is irreducible. And an irreducible curve D is called a component of C if its defining polynomial big Q, again with no repeated factors, determined uniquely by D up to scale, if its defining polynomial is a practor of P, and then D is contained in C, because if Q equals 0, then P equals 0, because Q is a factor of P. In fact, that's kind of if and only if. That is, if D is a subset of C, then D is actually a component of C. So since P has a factorization, P equals Q1 times Qn into irreducible factors. That's because C of x, y, z is a unique factorization domain. Then C is D1 union Dn, is a composition, is a decomposition of C into irreducible components. And okay, the factors are unique up to order and multiplication by units, which are the rescalings. Multiplication by units doesn't change the curves D, so that factor decomposition is unique up to order. So we can compute the order of the DIs, but otherwise this is determined uniquely by the curve C. So basically every curve C can be broken up into a finite union of irreducible curves. So this is a kind of general principle in mathematics. Let's say you want to classify or to understand some class of objects. Often you'll choose some kind of class of simpler objects into which you can break up the first things you thought of. So for example, finite groups can be kind of factorized into simple finite groups. So very often what you do is you find a way of factorizing something into simpler pieces, and then you try and understand the simpler pieces. So after you know that groups can be broken into simple groups, you then say, well, how do we classify simple groups? And there is an answer to that one. So let's look at an example. So the curve C, which is x, y equals 0, this is the union of two components, x equals 0, which is the horizontal part, and y equals 0. Do I mean that? No. X is 0 is the vertical part, y is 0, which is the horizontal part. And they intersect there at a point, and that point's a kind of nasty point. Okay, we'd like to know what kind of thing is it that goes wrong at this place where this curve is not looking like a smooth piece of the complex numbers. So that's our next definition, and this is something called a singular point. So let big C be a curve in CP2 defined by a polynomial big P of x, y, z without repeated factors. We want to give a condition on a point in C for it to look something like that rather than something like this. So we say that a point square brackets A, B, C in CP2 is a singular point of the curve C if, well, firstly, P of A, comma B, comma C is 0, so that the point has to lie on the curve, and the derivatives partial P, partial x of A and B and C is partial P, partial y of A and B and C is partial P, partial z of A and B and C. All of those three derivatives are 0. So why is that a good condition? Well, just as a just as an aside, let's look at P of x, y equals 0 in C2, and let's say P of AB is 0. So C can be that curve. Now then, if partial P, partial x of A and B is non-zero, you can use the implicit function theorem to write well, P of x, y equals 0 as in the form f of x comma x, well, sorry, f of y comma y, let's say, near AB as a graph where f, well, in fact you can take it to be a holomorphic function. So if one of the derivatives is non-zero, you can use the implicit function to show that you can write this curve as the graph of a holomorphic function in y, just in a small neighbourhood of the point. So it kind of looks, it looks reasonably smooth. And if dp by dy equals 0 of AB is non-zero, you can write in the form x, g of x, again for g holomorphic. So if one of the derivatives is non-zero, you can use an implicit function theorem to say that the curve looks like the graph of a holomorphic function, basically. Here we're saying we want all the derivatives to vanish, and that tends to mean that it doesn't look like a graph of a holomorphic function, it looks like something weird. So let's make a remark. Well, if P is homogeneous of degree D, then, well, if we differentiate, differentiating the equation p of lambda x and lambda y and lambda z is lambda to the d times p of x, y, z. We differentiate this in lambda. We differentiate with respect to lambda at lambda equals 1. Gives you an equation. The equation is that x dp by dx plus y dp by dy plus z dp by dz is d times p, where d is the degree. So this is called Euler's relation. So you should learn this. So the four equations I've written down there are not independent. Only three of them are independent. So hence, dp by dx at the point ABC is dp by dy at the point ABC is dp by dz at the point ABC is 0, and that implies p of ABC equals 0. At least over a field of characteristic 0. If you did this over some prime field, for example, then d might be 0 in your field. Okay, so this is a criterion we impose on points. So let's go back to our example of the axes. So let's take p of x and y and z to be just x times y. So again, this is the union of two axes, the kind of x-axis and the y-axis, but now we're in CP2, so there's also the line to infinity going on. So then, well, dp by dx at a and b and c is b, and dp by dy at a and b and c is a, and dp by dz at a and b and c is 0. So the only singular point is the point 0, 0, 1. And if you've got a curve defined by some polynomial, you can usually just find the singular points by solving several polynomial equations, and hopefully you find the answers. So it's an overdetermined equation, really. There's one more equations than there are variables if you take into account the homogeneity. So mostly you expect to have no solutions. Okay, so the only singular point is 0, 0, 1. So a singular point is where the curve is not smooth. In other words, it does not look like a small piece of the complex number. So you can't locally parameterize this curve in a small open neighborhood of this thing by just one complex variable. Something strange is happening. So a point of C is not, which is not singular is called nonsingular. You could also call it smooth. Yeah, well, perhaps I'll put that in brackets. And a curve C is non-singular or smooth if it has no singular points. So smooth curves are the nicest kind. We prefer them. They'll turn out to be Riemann surfaces in the sense discussed in the B3.2 course. Okay, so and then a singular point is where something goes wrong. And you can see from this example that even the topology of your, so that's your singular point. So even the topology of the curve at the singular point is somewhat different to the, is an open neighbourhood of that is not homeomorphic to an open neighbourhood of a point in the complex numbers. If you delete that point, it becomes disconnected, whereas if you delete a point in C, it remains connected. So let's make a definition. So let C be a curve in CP2 defined by our polynomial big P of x, y, z with no repeated factors. So that's determined by C up to rescalings. And let's suppose that square brackets A and B and C is a non-singular point of our curve C. So then the tangent line to our curve C at the point brackets ABC is the set of points x and y and z in CP2 such that x times partial p by dx at ABC plus y times partial p by dy at ABC plus z times partial p by dz at ABC is equal to 0. So this is a good equation. So that, and these are just numbers. So it's x times a number plus y times a number and so on. So this is a homogeneous polynomial of degree 1. Because we've assumed it's non-singular, one of the derivatives is non-zero because, well, we know that we have assumed that ABC is in the curve. If all of those three numbers are 0, then it will be a singular point, but we've assumed it's not. So one of these numbers is non-zero. So that's a non-trivial equation. So this is a It's a projective line in CP2. It's defined by non-trivial CP1. And that's since dp by dx at ABC, dp by dy at ABC, and dp by dz at ABC are not all 0. So as ABC is non-singular, okay, and by Euler's relation, the tangent line passes through A, B, C. Because Euler's relation tells you x dp by dx plus y dp by dy plus z dp by dz is d times p. If you put x and y and z to be a and b and c, then that will give you, well, a times that plus b times that plus c times that is d times p of abc, but p of abc is 0 because abc is on the curve. So the point abc itself satisfies that relation. And a kind of picture to have in mind is something like this. If that's your curve C, then the tangent line is what you think of as a tangent line. Let's give ourselves the notation T at the point to C. So big T subscript point of C. Okay, and so it touches C at the point A and B and C. So the tangent line is the line which best approximates the curve C at this point, in that it kind of agrees with the curve to kind of first order in differentiation. So it makes, the angle it makes with the curve is 0, if you like. Okay. Now, at a singular point, there may be more than one tangent line. So I'm not going to define tangent lines at a singular point now, but if you see sheet 2, question 6, I think, I haven't looked at the numbering recently, there is a way of defining tangent lines at a singular point, but then you may get several. And for example, at the point 0, 0, 1 in the curve C, which is x, y equals 0, the two tangent lines are x equals 0 and y equals 0. Okay, any questions so far?
How do we define the tangent line for singular point? We don't have.
Well, you tangent line for singular points. Well, you choose. Well, it does not choose. Well, so let k be minimal, such that, well, partial to the let's say L, partial to the I, partial to xi, plus j plus k, dx to the j, dy to the j, dz to the k of p at ABC is non-zero with I plus j plus k equals L. And then you look at some kind of well, you make a polynomial out of those derivatives of p at ABC, and it will turn out to factorize into what do I say? I think we probably say something like, yeah, you can look on the sheet, but you make a polynomial out of these, it factorizes into L factors, and those L factors are the, okay, you get L tangent lines such that the product of the line equations is built out of, you know, some kind of sum over I plus j plus k equals L, probably x to the I, y to the j, z to the k times this thing. And this thing actually factorizes into L factors because it's kind of a polynomial it's like a homogeneous polynomial in two variables instead of in three, because it passes through ABC to high order. Sorry, not a very good answer. Any more questions? In that case, I think we've probably had enough for today. Let's carry on next week when we'll be talking about conics, which are curves defined by second order polynomial in CP2.